So thank you very much. Yes, I'm Mark Mascheroni. I'm the co-coordinator of the CMS Submission Infrastructure Group at CERN. And yes, today the focus of my talk will be on efficiency and how to improve the pilot, the overall efficiency of CMS. So CMS is one of the two general purpose experiments at CERN that collects the proton-proton collision at the Large Hadron Collider at CERN. There are the collisions, the results of the collision are stored, distributed over several computing centers, then analyzed, reconstructed, and compared with the simulated Monte Carlo data. This generates hundreds of petabytes of data per year, and we leverage the worldwide LHC computing grid WLCG computing infrastructure to analyze this data. This WLCG is a federation of a collaboration of 170 computing centers and offering 1 million CPU, over 1 million CPU core and 2 exabytes in data storage. And in CMS, the group that takes care of managing these resources is the submission infrastructure group. We do that by operating instances of Glide WMS and Condor. In particular, we have the global pool where all the WLCG resources converges. We also communicate, we have regular meetings with the development team of Glide WMS and Condor. We communicate our priorities. And in practice, we operated a federated pool of 70 plus grid sites, plus non-grid sites, and using Glide WMS and Condor. I'm actually happy that we went through day 3 without the pilot or gliding. Glide is an implementation of a pilot, the Glide WMS implementation of the concept of pilot. I was a little bit worried that the pilot concept was not introduced until day 3 or 4, because it was in the title of my slide, so I was assuming the concept was known. But if you're new to the concept, a pilot or gliding is a way, the way Glide WMS uses to reserve resources on the grid, on external computing centers. The same technology used by the OSG pool. And it's what is used to launch and spawn an execute point on the flight. It has a limited lifetime. Speaking of the Condor pool that we manage in CMS, we have different types of access points. In particular, there are access points dedicated for central production, so small amount of people that collects the physics requests for all the physics group and generate ton of jobs using a tool called WM Agent. And there are schedulers that we give directly to user, either through tools like CMS Connect or through CRAB. And these are schedulers, access points that people use to run their job directly. We also have different types of resources, and we organize all the resources we have in different pools. We have the CERN pool with all the resources from CERN, which it's important to have a dedicated pool because we run the tier 0 jobs, which are the most important one that they run right after you collect the data. So you want to have a pool that is more stable. We have the global pool with all the WSCG resources. We even have a volunteer pool with people with their laptop can install Boeing and join this pool and dedicate their machine to science. And a pilot usually, this is the pilot district, a snapshot of the multi-core pool, both the global pool and the CERN pool, and how big are the pilots in our pool. You see you have a baseline of 8 core pilots. You have 10 core pilots, which I will explain later why you have these 10 core pilots. And then we have whole node pilot. This is mostly whole nodes, which we can use them transparently thanks to the flexibility of the late binding model that Condor provides. So we can just spawn up those requests and then schedule the job later. So having a big node, like whole node jobs, like up here on an 8 core pilot, which is the standard size of our resources, doesn't make any difference for CMS. And this is how a typical 8-core pilot runs. We run different types of payload. We can run 4-core, 4-core WMagent job. We can run different analysis job, CRAB jobs, and we have a limited lifetime of 48 hours. And if you want to calculate the efficiency of this pilot, you have to take the efficiency of each single job, so how much time the CPU was used by each single job, sum it, and divide it by the whole time. So this is how this efficiency is calculated. It is reported to WSCG, and there are metrics that are used to judge the efficiency or how well an experiment is doing by looking at the efficiency. There are different sources of inefficiency. We categorize them in two types. One is efficiency, the one in orange, that are coming from the scheduling. So with the way we schedule job, maybe sometimes we are not able to schedule job because of different reasons. Mostly it's due to the retirement time at the end of the pilot. At some point, the pilot has to stop. We stop accepting job. And this is usually around, for good site, the efficiency is greater than 95%. For the tier 1 is 97, 98%. Most of the inefficiencies comes instead from the payload themselves, which there are different reasons why a payload might be inefficient. I would say the biggest one is this one, the step chain versus multi-chain. So we execute all the steps a job has to do in one single job using a step chain. And we can also do the same. We can also do the opposite. So execute each single job of each single step of the job, the generation, the random number generation, the simulation, the reconstruction, the building of the AOD, all this kind of stuff can be either executed in one single job in different jobs. If you do that in different jobs, we are more efficient, but the turnaround is higher. It takes more time to deliver the data to the physics, to the user, because you have to run all the jobs at the same side, you have to reschedule, you have to stage out the output at every step. While if you run everything in a single step, you are faster. We measure that you have a 10 times faster turnaround. The consequence, what happens though is that when you use the step chain, you run all the steps in one job, you might have that you introduce inefficiency because there might be some steps that are not using all the cores of the job, the 8-core or 4-core that the job is asking efficiently. For example, we have some random number generator that are inherently single core and they cannot be, or maybe they're using old code that people need to use old code to analyze the data, and this old code is not optimized to run the full 4 cores. So the question is, can we maintain this flexibility because all these reasons are hardly reducible. All these reasons of sources of inefficiency are hardly reducible. Can we do something else to improve the efficiencies of our pilot? And this enters the idea of the overloading. So the idea is to still run an 8-core job, but allow to schedule 2 extra core on top of this 8-core pilot. This way we can, when one of the jobs maybe is using a single core random number generator, you have 2 extra jobs that can use the CPU. This is trivial to implement because it's a configuration parameter. It's hard to verify and make sure that we are not doing anything wrong and this works and do the analysis. And for example, one thing that can happen is that there are some stages where all the 10 cores are wanting to use the 8-core that are available, and you might get the job goes slower. So this there are also considerations about memory. Well, I'll skip this slide in the interest of time, but the key concept is that we have enough memory to overload also the memory and keep the 2 gigabytes per core ratio that we are using as our basic compute unit. This is an example of a whole node slot. It's a pilot at Fermilab that was running for 2 days. It was running, the machine was 128 cores, but we overloaded it to 160 cores. And you can see here, this pink one is a workflow that was 75% efficient. We measured the efficiency of each one of the workflow. Each color is a workflow. It's starting here running some jobs. Here we are running probably 24 core jobs, so 80 cores. Each one of the 4 core jobs is 75, on average 75% efficient, and we are able to recover some CPU cycle by the overloaded.
A quick question here. Did you consider using nice values for the overloading, or
other values, you mean?
I don't know. In the old days, they called them a nice value.
Nice value.
Different. We even had a version that we called the Bologna batch system.
We considered that. We did some experiment by tagging the 2 extra cores as special slots and with nice, but in the end, we don't think it's worth, because
it's not worth.
Yeah, especially if with Greg's presentation yesterday, we at some point we will have C groups V2, and we'll be able to put the pilot itself in a C group, and that's
got it.
The
okay.
operating system will take care of that. That's our plan. Right now, we don't have we have not done that. So some result, this overloading was enabled early in 2023 on a few sites, PIC, Siena, Tendesi. We enabled that only on half of the resources, so each site has multiple compute entry points. We only enabled it in half of the compute entry points. You can see there was, in the chart, you can see as soon as we enabled the overloading, the efficiency reported to this is the efficiency from the portal, WLCG port, it's the EGI portal. So this official efficiency is reported to WLCG. Given the good results, we extended the number of sites that we are overloading in January 2023. We extended it to the tier 1 and a set of good tier 2. We kept the same strategy of keeping 50% of the resources of the compute element unchanged, and we are at a point now where this is a picture of the global pool. We are at a point where we are half of our resources, a little bit less, are from overloaded sites. So this is the efficiency for I took since the EGI portal doesn't have data for all the sites, the breakdown for C is not available for all the sites. I took the data from our pilot logs where the efficiency is reported, and I calculated the differences between sites. I was able to do that only for 8-core pilot for the moment. We ask for support for whole node, also for the future, because the CPU. Because for all node, you don't know how many cores you have. So we ask the control developers to add this information in the pilot log so we can compute the efficiency also for the whole node. This is data from the last 3 months. We didn't observe any impact on the failures of the jobs. And where we observed an impact is on the invert rate, for the reason I explained before, where that if we run we pack too many things in a same envelope, things will go slower. And this is a picture with where in the y-axis we have the event rate, and on the x we have all the sites where for each site we have 1 bar for the overloaded and 1 bar for the non-overloaded. We have measured the average event rate for all the jobs running at one site for a particular workflow. This is still data from April, May, June, and we have taken one particular workflow. It was the one with most jobs. It was 450,000 jobs in total. and the average event rate is measured for each site, and the bar, I also measure the standard deviation, which is the bars. You can see that there is an impact. In general, the overloaded C jobs are going a little bit, the average is a little bit lower, but it's comparatively small if you compare it with the standard deviation, or even if the difference between side by side is not a big number, big impact in the terms of event rate. This is another workflow, different type of workflow. The one before was a Monte Carlo simulation. This is a data processing that actually is processing the data. It was 20,000 jobs. As you can see, it's a very different event rate. So it's not possible to calculate the event rate of the whole pilots, not simple. I have plans to do some experiment by forcing a single workflow to different pilots to dedicate experiment. But in general, you cannot measure the event throughput of the whole pilot. You have to really go by site and workflow combination, because we have very difference in the event rate, but even by sites and by type of workflow. So in conclusion, CMS has been operating the biggest IT condor pool since 10 years. We have an average of 350,000 cores in our global pool and 400,000 cores. In total, we execute from 1 to 10 million jobs per day. And today I show that we have applied this strategy of overloading our pilot, which allow us to gain 5 to 20% more event cycle, which correspond to 30,000 extra core without having an impact on the job error rate, and by sustaining a small impact on the event processing rate. And that's all. And of course, many thanks for the HTSS team for the help and the fruitful collaboration over the years. That's all.